that better? Okay, good. Alright. So yeah, we've been at Parfait for a number of months now, and we'll be presenting finding bugs in open source kernels using Parfait. So on agenda for today, so I'll give you an overview of bug checking in general. We'll talk about static analysis tools. I'll then discuss the Parfait project. We'll show the kernel results, and then I'll hand it over to Christian to do some Parfait evaluation, a demonstration, and we'll finish with a summary. So in development, basically, we face a challenge of bugs. And so as you can see, we try and get rid of these bugs as early as possible in the development process because it's cheaper. So we never do produce perfect code, even though some of us may think we do, and we employ a number of methods to get around that. So we've got testing, code review, dynamic analysis and static analysis. These all have different pros and cons, and they're all implemented at various times during this process in order to get rid of these bugs. So testing in particular has a limited code coverage, basically because they're a synthetic type thing, and they can only be as good as they're created. And they're very costly to create and maintain, so a lot of man hours go into keeping these up to date and working. On the good side of things, they've got excellent regression testing, so if someone breaks the code, you usually know fairly soon from running the test cases. And they're usable fairly early in the development process. Code review is not automated. It can be very effective but also time consuming, and that's also used various times throughout the development process. So dynamic analysis traditionally has a very small code coverage, so that's basically because we've got a fairly typical run when we do the analysis, so not all branches of the code paths are explored. And we also see a significant slowdown, so from around 10 to 300 times, depending on the type of the program. Static analysis, on the other hand, has good code coverage because we aim the entire code, and we can detect bugs before executing or deployment, so before they're shipped off to users. The issues that they face, however, are scalability and precision. So onto static analysis tools in general. So they started around 1978 with things like lint, and these were based largely on pattern matching, and would basically warn about potential problems and unsafe usage. So pretty similar to what we see GCC doing now with warnings and errors and things like that. Second generation bug checking tools came about in around 2000, and basically the difference is we detected errors that can occur at runtime and will be bad. Another big difference between the two generations is that we're starting to use static analysis techniques. So these are some of the bug detection tools available. So you can see there's quite a few, mainly focused at C and C++, from commercial and open source, and from industry and universities. So the scope of static analysis tools, what we focus on is implementation errors. So things like buffer overflows, memory leaks and things like that. So these are things that are basically the developer's fault, and everyone's been tricked up with pointers, even if they don't admit it at some stage, or indexes or something like that. And these are often things that can't, or they sneak past a compiler or warnings, and you don't pick them up until later on. So that's what static analysis tools target. What we don't look at, however, is logic errors. So this may be obvious, but it's basically because we don't know what your program's supposed to do, so we can't tell you that it's wrong. So logic errors are left more for testing and things like that. So all of these tools face barriers to adoption, and those barriers are scalability and precision. So when I talk about scalability, I'm basically talking about how feasible is it to incorporate this tool into my build process. So if we're talking about code bases with very large amounts of code, basically it becomes infeasible if this tool takes way too long to run. And let's face it, if the tool takes 2 or 3 days to report back, it's basically reporting old information that we probably don't care as much about. So the other one is precision. So precision is to do with the actual reports, and because the way the analyses work, we make approximations, and what can happen sometimes is we generate a false report or a false positive. So these false positives basically say, in one of your .c files, you have a bug here, and it's doing this. So what happens is the developer or whoever has to read all these reports from the static analysis tool goes through and says, oh wait, this isn't a bug. So the more of these false positives or false reports we get, the more overhead there is for the poor developer to go through and may only find 1 in 5 bugs actually worth fixing. And as you can imagine, if we're generating thousands and thousands of reports on large code bases, then it's a huge overhead, and once again it becomes impractical and useless. So onto the Parfait project. So in case you haven't guessed, it's a static analysis bug checking tool. And our aims, as I touched on before, of course, are to be scalable and precise. So Parfait was actually started to scan the larger internal systems code, and yeah, targeted mostly type unsafe C and C++ code, large code bases, and we want it to be scalable and precise. So this is how we intend to achieve this. So basically the way Parfait works is you start off with a potential list of bugs. So for example, if we take buffer overflow, things that would make the potential list would be any accesses to these buffers, indexing and things like that. We then have a potential bug. So once we generate this list, we run over a series of analyses. So these analyses all differ in complexity. So the idea is that we start off with the simplest form of analysis, and that way we're using a very simple and cheap analysis to eliminate as many potential bugs as possible. We then move on to more complex analyses, and we hope that the potential list is shorter by the time we run the more complex analyses. So once we get down to say PA3, for example, we've eliminated as many potential bugs as possible, which means less work for the more complex analysis. So overall, more sleek design. And of course, these analyses sort the bugs into real bugs and no bugs. So that's how we generate the actual report. So these are the analysis techniques that we use. Currently employed, we've got 3 for buffer overflow, and a few more for other bugs, and we've got a few more on the way in development. So the first and most cheap analysis technique is constant index checks. So you can see here in line 5 we've got a buffer of size 50, and then on line 1 we're declaring that buffer, and on line 5 we're accessing that buffer with a constant index. So basically the analysis will just check for a new buffer, keep in mind the size of that buffer, and then keep an eye out for any constant dereferences of that buffer. So you can see here it's basically going to compare the index in line 50 to the original size and say yes, we have an overflow here. A slightly more complex analysis is partial evaluation. So you can see in the top box we've got the same buffer, and instead of using constant index we're using I inside a for loop, and I is restricted to be less than or equal to 50. So the first thing partial evaluation will do is generate a program slice. So that's denoted by the second box there. Basically we've got the same for loop, however all the stuff inside the for loop has been replaced by this if statement. So the if statement is derived from the constraints on the for loop and the size of the buffer. So we know now with this if statement what is an acceptable size for the buffer, or rather what is not an acceptable size for the buffer. So if I is less than 0 or I is greater than 49, then basically it's going to be out of range. So what partial evaluation will do is run this, and if true is returned, then we know we've got a bug because I is out of range. And it doesn't actually have to worry about the printf statement and the things in between. And then of course if it returns false, then we're okay. So the third analysis targeted buffer overflow is symbolic, and this is our most complex analysis. So you can see in the top one, the top box, we've got n, and n is dependent on the command line. So we don't really know what it's going to be until runtime. We've also got a buffer of size n. We're running through a for loop constrained by n as well, and we're indexing that buffer using I. So in the second box, you can see what symbolic analysis is actually doing. And it's denoted on the right hand side by the comments. We declare n from the command line, and like I said, there's no way of knowing what this is actually doing. So what we do is we adjust the bounds of n to be variables, so n to n. Then we go down to line 3, and we've got I equals 0, and we're dereferencing with I on the right hand side there. So we adjust those bounds to be from 0 to 0, and then straight after that we've got I is less than or equal to n. So we've got an upper bound now, so we adjust accordingly. And of course it's n plus 1 because we've got less than or equal to. And then when we've got buffer on line 4, we can compare the range of the indexes to the range of the constraint and see whether or not it's actually going to cause an error. So that's how symbolic works. So this is one of our analyses not targeted at buffer overflow. So basically standard C library checks checks the preconditions in standard C library function calls, and basically just checks that these preconditions won't cause a silly error. Format string analysis deals with all the printf, scanf, input, output type stuff. So you can see here we've got a wrong type example. We've got a %x passing in 3.0. We've got too few arguments because we've got a %s with nothing there, no variables. And then we've got a size incorrectness, so basically because we've got a character. So on to the kernel results. So this is how Parfait is actually implemented on a higher level. So we start off with an input C program, and then we run over Parfait GCC. So Parfait GCC is actually a wrapper for the regular GCC compiler, and basically we drop it in as you would drop in a normal compiler into the input C program's usual build process. So then we build the program using Parfait GCC, and we generate what's called bytecode files or .bc files. So once we've generated these BC files, Parfait then does its work and generates reports with real and false bugs. So an important note about the bytecode files. The reason these are around because Parfait is based on top of LLVM, which stands for Low Level Virtual Machine. So basically inside the bytecode file there's just a number of instructions which are all derived from the LLVM instruction set. So Parfait uses these to perform the analysis. So what we did was run Parfait over all these open source kernels. So this slide denotes the scope of what we've tested. So in OpenSolaris, for the core, we've scanned the UTS directories and all the IO files for the drivers. For Linux, we scanned the complete distribution and the drivers and sound folders. And BSD, we did the sys folder and dev for the devices. So these are the results. So you can see it's split up into core and device drivers. That's mainly because we found a lot more defects in the device drivers. You can see the non-commented lines of code there as well. Number of buffer overflows. We can also see bug density, so that's number of bugs per 1,000 lines of code. And of course the status because we've submitted the bugs. So interpreting these results, it's not a straight up score. You can't say, yeah, this operating system is better than the other. There are some factors to consider. The first is what I touched on before, so that is that defect rates in device drivers are an order of magnitude higher, so significantly more. I'll leave it up to you guys to speculate why that is. And we've also had Linux scanned by other static analysis tools, so namely Covariety. The bugs that were on the previous slide we found, so I don't know whether that gave Linux an advantage or not, but I suppose it's noteworthy to mention. Okay, so I'll hand you over to Christian now to talk about the evaluation of Parfait.
So in order to ascertain that the goals of scalability and precision for Parfait are met, we've designed 3 benchmarking suites. But before we get into these suites, we'll talk about some of the terminology we use when it comes to benchmarking. So firstly, if the tool correctly reports a bug in the program, we call that a true positive. If the tool reports a bug that doesn't exist, so a false report, that's a false positive. If the tool fails to report a particular bug, that's a false negative, and we're not too concerned about true negatives here. So if we look at the ratio of the number of bugs correctly reported by the tool to the number of bugs that the tool has missed, then that's recall. And if we look at the ratio of the number of bugs correctly reported by the tool to the number of incorrect reports by the tool, then that's precision. And accuracy is a combination of precision and recall. Now the first suite that we've developed is the Synthetic Suite. So it consists of 1,691 benchmarks, and they're all synthetic code, so quite small, 88 lines of code on average. Now these benchmarks were extracted from the works of Krakowitz and Samate. As you can see in the table below, we have run several tools over these benchmarks, including Parfait, Splint, Clang, and Uno. And for each of these tools, we report the bug types that these tools support. So for example, for Parfait, 869 correct bugs have been found and 184 have been missed, but there were no false reports over that suite. So that gives Parfait an accuracy of 85.7%. For tools like Splint, there are usually more false positives, which results in a lower accuracy. We should note, however, that we didn't use annotations in the source code. We also didn't have access to any of the commercial tools, so that's why they're not listed here. Now the next suite is the Nonsynthetic Suite. So this consists of source code extracted from Sitzer, Lou, and our own work, and essentially it's extracted by looking at bug reports from various applications such as Apache, KDE, MySQL, etc. Again, we've ran the 4 tools over this suite, and you can see the results in the table below. The main thing to note here is that the accuracy for all the tools is significantly lower because these are actual code examples and they're quite significantly longer than the ones in the previous suite. So as you can see for Parfait, for example, we found 53 true positives, but we've actually missed 118. So the recall is significantly lower. But nevertheless, we have no false positives, so the precision is good. Now finally, we have the Scalability Suite. So you can hopefully see we've got 9 applications, things like MySQL, GCC, Perl, etc., and they're varying sizes. For each of these applications, we have, first of all, in orange or yellow, the build time, which is the time essentially for GCC to do a normal build of that particular application. The other thing that we have is in blue, the Parfait build time. So that's the time for Parfait to generate the bitcode files. And in red, you can see the analysis time, which is the time for Parfait to run over the generated bitcode files. Finally, in green is the time for Splint to process that particular benchmark. So we're going to move on to a demonstration. Firstly, we'll start off with the command line interface. So if you look at this small little program, the first thing you might notice is on line 9, here, we have a use of gets, which is a pretty straightforward error. And then on line 11, we have a constant index error. So in this case, the index is buffer size, which is only ever modified up here and set to 50. So with constant folding, with trivial constant folding, we can determine that at this point here on line 11, we're accessing buffer with the index 50. So if we now run Parfait, so the first thing we have to do is run Parfait GCC to generate the bitcode files. We then run Parfait over the generated bitcode file, so a.out.bc. We're getting a number of reports here. So the first report, so in here we have this use of gets. So it's a buffer overflow. It occurs in demo.c on line 9. The function is main. The analysis that's counted is constant index checks, and the specific error is the use of gets with buffer. The second error here is the one that's solvable using simple constant folding. So on line 11, the expression is buffer with index buffer size. Now if we go back to the source code here, on line 14 there's a while loop, so it's pretty straightforward while loop while I is less than buffer size. The problem with this loop is that on line 15, I is incremented before it's used in the dereference on line 16. So essentially, I can be equal to buffer size on line 16. So if we look back on the error here, this can be found with partial evaluation. We see that Parfait reports this error in the dereference of buffer I on line 16. Finally, the last bit of code here, essentially we have a relatively standard for loop here. The problem with the loop is that we're accessing the buffer with j+1. So this is something that symbolic analysis can find. If we look back at the error report, we can see that this read buffer overflow, the index is j+1, and we're told here that j+1 is less than or equal to 50, so it can be equal to 50, which is the buffer size, array size here, 50. Now, having looked at these, we'll look at an actual example. So let's run Parfait over. Let's run over XPV. So this is an example from OpenSolaris, and as you can see, Parfait has reported multiple errors, but they're essentially the same error occurring on multiple lines. So if we look at this one here, for example, what it's saying is that on a line 118 of the file evtchn, there is a buffer overflow in this expression. So the index is evtchn, and the array is evtchn two-handle shown here. So if we look at this file, on a line 118, we can see the expression here. So the first thing we might want to do is figure out where this variable is defined. So this array, if we go to line 43, we'll see the definition of the array shows the size of the array being number event channels. So if we go back to line 118 where the bug was, if we now look at this index variable, evtchn here, we scroll up a little bit for the next relevant use of this variable. It occurs in this if statement here. And the problem is that an error is given if evtchn is less than 0 or greater than number of event channels. Now, that means that evtchn can be equal to number of event channels, causing the buffer overflow on line 118. Finally, we'll run over an example from Linux. So now with this one, it's saying that the error is in MPU for a 1.c line 1086, and it's a sprintf error. So it's a sprintf, and the buffer involved is given here, MPU since info m.name. What we're going to do here is look at the actual GUI, because it's much easier to look at bugs in the graphical user interface. So if we look at this GUI, so the first thing we have here is an overview slide, which shows the different bug types and their proportion in the code. So you can see read buffer overflow, 32.9%, and so on. If we want to look at the actual specific bugs, we click on the Bugs tab up here. So now we have a list of all the bugs. For each bug, we have a unique identifier, the type of the bug, the line it occurs on, the file, and the function, which you can't really see here. So the function is all the way over to the right. If we're looking for a specific bug, what we can do is type in here and filter it. So this is the MPU 401 bug that we saw in the command line. Now, in order to investigate this bug, we can click either Investigate Bug or double-click on the bug. That's readable. So we go to the line 1086 where the error occurred, and we can see the sprintf here. So we Hopefully you remember the array variable that was used is this one, and the actual format string is given here. So as you can see here, with this format string, if we assume that the size for each of the format specifiers, so %d and %c, is at least 1, then we can trivially compute that the size of this format string must be at least 30, plus we need to add 1 for the terminating null, so that makes it 31 characters in length. For some other cases, you might need to do more analysis on %ds and %cs, but here it's not necessary. So we know that we need at least 31 characters to be the size of this name array. So the next thing we need to figure out is essentially where MPU since info is defined. In the GUI, it's quite easy. We simply look at the dependencies, so we can scroll up, and you'll see that the files are collapsed so that you don't have to scroll as much. And the first relevant dependency is the definition of the variable that we're looking at, MPU since info. So we can see here that its type is struct since info. So the last step that we need is to look where struct since info is declared. So this is actually in a separate file called soundcard.h, and you'll see here the declaration of struct since info. And specifically, we're looking at the name member, which is declared here to be of size 30. So that's why when name is used here, the size is of 1 at least. Other things you can do is flag bugs as favorites. And you can quickly reference them here. So that's very useful. And the final view essentially lists the different files in the directory structure of your source. So if you go to view containing file, or if you click on the files tab, you'll notice the directory structure down the bottom here. So look at some of these. You can click on the various directories and move through them, and you'll see your bugs listed here. So this is the file, and there's the bugs. You can move through the bugs by clicking here, and recent files are cached for you there. Having had a look at these, we can look at OpenSolaris. So again, we have the overview here. What we can still do is change things like showing them by type, or by status, or by file. Or we can generate a new plot if we want to. So in this case, for example, we can look for all the bugs in the Intel subdirectory. And in fields, so we look in location, and unfortunately, let's hit the apply button here. So we can see most of the bugs are in the Intel subdirectory. Apart from that, we still have the OpenBSD data. So if we look here, again, we can look at these various things, and we can change the graph to be a cloud graph if you want some different looks. So is that better? That's pretty much the demo. What we can still do is look at the other bug that we had in OpenSolaris. So if you remember, this one was in a file called EVT. So you can see there's 4 of them here on different lines, and we looked at the one on line 118. So if we go to line 118, hopefully that's large enough. So you can see the expression here, and it's much easier to go back up to line 43 here, where we can figure out what it was defined to be. So it's much easier to determine that we have indeed a bug. Now that's pretty much it. Anyone have any questions so far? Yep. So essentially, we're still working on multiple analysis, and also there will be a binary release at some stage in the future. And apart from that, it's undecided. But we're still working on different analysis and so on, improving symbolic analysis. Yep. Well, it's still undecided. But if you check our website, we'll give you some updates. Actually, I should probably do the summary slide. What was the question over there? Yep. Well, you'll have to wait. It's not decided yet exactly what's going to happen in that part, but I guess. Depends. Not decided as of yet, I guess. So, yeah, so to summarize, Parfait is a scalable and precise bug checker, and it's starting to be widely used internally. So we have met the goals of precision and scalability. We've mainly been emphasizing on things like buffer overflows, pointer memory errors, format strings, and others are coming. And we have found real bugs in different kernels, but also other applications. And you can see some of the links here if you want some bug reports. Yep.
I did one. Yeah. Next question.
So have we what run over GCC? Yes, we have. Yes. Well, we haven't actually verified all the bugs in GCC. So what you can see here on this graph is GCC here with about 474,000 lines of code as we compiled it. But we haven't actually manually checked all of them for all of these applications. Although we get low false positives, it's still a fair bit of work to essentially look at all the bug reports, and we haven't had time. I mean, for this harness, we've mainly focused on the actual time it takes to scalability. So we have the bug reports there for GCC, but they haven't actually been manually verified yet. Have we been what?
Yeah.
Yes.
Yeah, well, in the status, like, that's where they're at. Obviously, we don't publish them, but we tell them to the right people, so that's okay.
And you should be able to.
That's why I said the thing with the score, like, interpret the results how you like.
Yeah.
Don't blame me.
So.
Yeah.
And there is some links here to the bug records if you're interested. So we have some links there for you, and there's a link to the project website where you can look for updates and notice on any releases. Yep. Essentially, yes. So there's slight extra code that we compile into it in order to keep track of some of the things that are lost in LLVM, essentially. But pretty much, yes. Yep. Well, I mean, I guess I can see where you're coming from, but there is kind of a fundamental design difference between, say, a plain executable and an LLVM bytecode file. So at the moment, we don't really have the support for running over normal executables. Yep. Yeah. Yeah. So, So I guess, I mean, if you got the supplier to give you the properly compiled bitcode files, then yes, we'd be able to run over those without a problem. So if they ran Parfait GCC instead of their GCC or whatever, and generated some bitcode files, then we'd be able to run over them easily. Otherwise, I guess with an XE, you could still decompile it, but obviously you lose all the debug information, and you'd have, yep. Yeah.
Consumer, yeah. So pick something off the shelf, yeah. So I can see where you're coming from. Yeah, no comment. Especially with the green tools,
Yeah.
Well, I went through and verified a lot of these bugs to see where they come from. Interesting thing, some of the bugs are very simple, like some of these kernel strings, because the minus for 0 and what it's surprising. And like I said, there's millions of bytes for them. I can't actually been paid since I've come to look at it, but yeah, there was a couple of important bugs inside the actual core that probably going to security. So yeah, I can't remember off the top of my head, so I'll let you know. Yeah, right.
Yeah.
Yeah.
Yep. Well, I mean, so we have C, C++ support. I guess LLVM, being a portable instruction reference, would lend itself to supporting other languages, but it's not really a priority at the moment since we do focus on system code. But it's certainly, I guess, a possibility. I mean, since we do use LLVM, which is portable and has compilers available for other languages, it's certainly a possibility, yes. Anything else? Oh, thanks. Okay, so